Okay, so this is a Zong-Gang Mou. I'm now a postdoctor in Rice University. It is my pleasure to present our recent work, Electromagnetic Bursts from Merger of oscillons in axion-like fields. The work is done in collaboration with Mustafa, Amin. Okay, yeah, our motivation is simple. We know axion and axion-like fields are well motivated in theory and in cosmology. They are the candidate of dark matter. They interact weakly with the standard model particles. Such weak interaction imposes difficulty in detecting the axion, especially from the lab. So the aim of the paper is to provide and to simulate a scenario where even the interaction is feeble, we can still observe dramatic effect. In particular, we will consider explosive creation of photon due to parametric resonant from the merger of two dense axion stars. It is well known that the axion will modify the Maxwell equation. To say the exponential, to see the parametric resonant, we can first look at the homogeneous axion background. In this case, the Maxwell equation can be simplified into the equation motion for the gauge potential. And we say if there's an oscillating axion field, there will exist a parametric resonance. In inhomogeneous axion background, the situation becomes more complicated. But this is also the place we are interested in. This is because spatially localized axion configuration are more relevant to astrophysical observation. In particular, in this work, we will consider the merger of two axion stars. Without gravity, the axion stars, also known as oscillons. Before we go to the merger of two oscillons, let me just explain briefly what is oscillon. So oscillon is scalar configuration, which can long-lived, coherently oscillating, and spatially localized. Oscillon can exist even when gravity is not included. So in this work, we will not consider gravitational interaction. We will only consider self-attractive interaction. Also, we will not consider the standard cosine potential for axion. Instead, we choose tangent potential. This is because such a potential can provide a long-lived oscillon. Within such potential, then the oscillon can be characterized by the frequency omega. We can separate the oscillon profile into radio profile and oscillating part. In particular, the radio profile also depends on the frequency omega in a way that if we know what is omega, we can determine the radio profile. Vice versa, if we know the radio profile, we can also determine the frequency. Within the potential, there exists a very special frequency, which is 0.82. In a way that the oscillon will spend a larger fraction of its lifetime oscillating in such a frequency. So quite likely, if we observe an oscillon, we will observe it oscillating at this frequency. So with this reason, we will stick with the special frequency. Now, with the setup of oscillon, we can go forward to study what would a photon react to single oscillon background. In this case, we can look at the luminosity. In this plot, as we say, there are exponential growth. We can extract the exponent of that exponential growth. We defined mu effective. As we say, the mu effective depends on the coupling constant in a way that if we increase the coupling constant, then that mu effective is also increased. On the other hand, the mu effective also depends on the configuration through omega, in a way that if we increase omega, the mu effective is decreased accordingly. So now if we put all those into one plot, we plot mu effective against the coupling constant, then we notice there exists a linear relationship. And if we extrapolate such linear relationship, then we will obtain a 0 point. We call such 0 point mg gamma critical. Mg gamma critical will separate the parameter space into two parts. In the region with a value larger than the mg gamma critical, there exists a linear relationship. Below the region, below mg gamma critical, there's no exponential growth. Also, we notice the mg gamma critical will depend on the oscillon configuration through omega. In this plot, we show two different omega. Actually, we do this purposefully. This is because those two frequencies will both appear in the merger of the two oscillons. So here is the time for a movie. This is the collision and the merger between two oscillons without a photon. As we say at the end, we can obtain a new oscillon. We can also see the process through the snapshot of the merger. The phenomenology of the collision and the merger between two oscillons is very rich. Here we consider the simplest case, which is head-on collision. And those two oscillons have the same frequency and with the same phases. The result of a merger is a new oscillon. We can extract its frequency from its radial profile. And the value we obtain is omega around 0.76. And with this number, we can estimate about 30% energy is lost to scalar radiation during the merger. Now, back to the plot of mg gamma critical. There exists an interesting window, the region between two mg gamma critical, in the sense that if the parameter is chosen in this region, then we will see that initially, before the merger, there is no exponential growth because the value is below mg gamma critical of the initial oscillon. But after the merger, there will exist an exponential growth because now the value is above the mg gamma critical of latter oscillon. So this is the guideline that we stick to choose the coupling constant. Now, with everything ready, we can assemble to do the full simulation. This is the result of energy density over XY cross section. The left-hand side is about oscillon. The right-hand side is about photon. As we said before the merger, there's nothing happened to the photon, but after the merger, there are photon bursts. And we can have a better understanding from the snapshot of the process. I should emphasize that this is a full axion photon system. We include the backreaction of photon, and also we let the simulation run long enough so that at the end, we can also see the end of the resonance, which we can tell from the last column that at the time around 350. For the exponential growth, we can look at the luminosity. And this is the luminosity of the photon. Roughly, there are 4 epochs, namely before the merger, there's nothing happens. And in the collision and the merger, the physics in this epoch is complicated. As you can see, there's some bump. Afterwards, after the merger, we see their exponential growth. And if we let the simulation run long enough, then we can also observe the end of a resonance. At this period, the frequency of the oscillon is increased to some value that the oscillon ran out of resonance. In the whole process, 20% energy is lost to photons. Okay, now we can have a better understanding of created photon from the photon particle number distribution. As we can see, the generated photon has a frequency roughly of same order of lowercase m. And also from the particle number spectrum, we can also observe some feature related to the omega, the oscillon. Here, we provide some number might be relevant to observation. The energy transferred to photon can be estimated to such amount, and the frequency of created photon is of same order of mass m. And also, in the paper, we also provide the rate of event. Okay, in summary, we simulated the coupled axion and the electromagnetic field, including backreaction of photon, to demonstrate the explosive creation of photon due to the parametric resonance from the merger of two oscillons. There are several features in the process. As we say, there is no significant radiation to photon from initial oscillons. But after the merger, we can observe photon burst. And also, we can see the resonance can be closed due to the backreaction of photon. In the whole process, 30% energy is lost to scalar radiation, 20% energy lost to photon. We have considered possible application of our work is faster radio bursts. Also, we want to include the gravity in future work. Thanks for your attention.